Hi, I'm Stephanie Thomas, an engineer at Princeton Satellite Systems, and today I'm going to walk you through an example of an isothermal model of a spacecraft. This is an example from the thermal module of our Spacecraft Design Toolbox for MATLAB. The first step in thermal analysis is to model the spacecraft as a set of areas with specified surface properties and to treat the spacecraft as a single mass. This is done in our toolbox with the isothermal function. The header is shown below. This is a live script in MATLAB, which shows the output inline. Here we see the inputs are going to include orbital elements, the name of the orbital center, the data structure defining the spacecraft model, and the date in Julian date form that we're going to be doing the simulation for. The header includes the reference. The spacecraft is defined by its illuminated area and its radiator area, along with its coefficients. And this example is going to approximate a 1U CubeSat. First, we use an average density to estimate a mass for the satellite. Then we're going to get the default data structure, defining the spacecraft model by calling the function with no inputs, as you see here. We specify the area and properties of the areas, temperatures, and the average specific heat. This is the data structure printed out to the command window. Now we're going to model our spacecraft in Earth orbit. This is done with a set of Keplerian elements here with the semi-major axis, inclination, and 0 for the remaining elements. We have a 370 kilometer altitude, and we're going to do 1 day. This is Julian days, and we're going to plot the orbit. I just reran the section, and now you see our orbit. We're going to define an oscillating power model with 10 watts plus or minus 2 watts. And here in this section, we call the model isothermal with our elements, the planet Earth, our data, our array of Julian dates that we calculated. And as you can see here, it plots our isothermal temperature, starting at 300 Kelvin, going up to a little above 340 Kelvin. This is hours. It computed that x-axis automatically from our time. You can see our flux in watts coming in here, our solar flux given our orbit, our orbital position, the planetary data, the albedo. This is the sunlight reflected off of the Earth. The radiation comes from the Earth in infrared wavelengths, and eclipse fraction shows us that our spacecraft is seeing eclipses. We can easily do the same analysis for Mars orbit by creating new orbital elements, calling our orbit function, and then our isothermal function with a Mars orbital center. And after a second, we have our Mars figure with our same altitude orbit. And our temperature was a little less. We can see that the flux is a lot less, given that Mars is further away from the sun. The power, this is the power dissipated within the spacecraft bus, is the same. So that's between 12 and 8 watts. And this just confirms our orbit. This is the planet's position relative to the sun. Now the albedo is the sunlight, again, reflected off the planet. So that's only when the planet is on the sunny side, or when the spacecraft's on the sunny side of the planet. So you can see here that during eclipses, that's 0. The planetary radiation is constant across the orbit. And here's eclipses. Our eclipses were shorter since Mars has a smaller radius than the Earth for the same orbital altitude. And now finally, we're going to run the same model in heliocentric orbit. We're setting our spacecraft at half an AU, which is half the distance of the Earth from the sun. This is our trajectory in kilometers. We're going to run in this example now for 30 days. So LinSpace creates an array for our number of data points. And here we can see that when we ran it with our center as the sun, our temperature increased to over 400 Kelvin because this is much closer to the sun. The flux is over 5,000 watts. And the power, again, is from 8 to 12 watts. That's dissipated by the satellite. And that's the end of our demo. For more demos, go to our help website. Thanks for watching.